Hi y'all, welcome back to another vector video, and today we're going to be covering vector multiplication. So vector multiplication, we'll just put vector mult. And you say, wait a minute, we've already done that. Yes indeed, thank you for remembering our past videos. We've already covered the idea of scalar multiplication. In other words, I take a scalar, a single number, and I multiply it by a vector. I'll just say times a vector. We've talked about if the scalar is less than 1, you end up shrinking the vector. If it's greater than 1, you end up expanding it. And so if you don't remember any of that, I'd say go back, look at the next video, and come back to this one. So today, or at least for this video, we're going to actually cover what's called the dot product. I'll save the cross product for the next video, but this is a different way of doing multiplication using vectors. And to give away the final ending, it's you multiply two vectors, and at the end you get a scalar out. Now this is really important. For example, if you're doing something like calculating the work done by a force. And if we won't go into the details of this, this will be several chapters down the road, but the idea is let's get the mathematical stuff in place first. Then when you run across it, you'll say, okay, Greg talked about this in the first week. I'll go back and watch the video or go back and remind myself. It's an idea about let's get this out of the way first. Let's get some familiarity, and then when it pops back in, you'll have it for you. Excuse me. So let's get off and rolling here. I'll start off with the graphical interpretation, but let's get rid of this. We'll start with the graphical interpretation. So let us say for a moment that we have two vectors. We'll say A and B. So let's draw our vectors in here, A and B. Nice, lovely vectors. We'll say B is right here, and we'll call this vector A, and let's give A a direction. So graphically, how do we go about doing the dot product? Well, we're going to take advantage of the idea that we can translate vectors. So let me grab vector B, and I'm going to translate it. And here you'll notice I'm going to actually translate it so that the tail of vector B coincides with the tail of vector A. So we'll drop it right there. Perfect. So now I've got my two vectors arranged in order to do my dot product. Now, how you could think about the dot product is this is one way of thinking about it. It's finding the component of B that is in the same direction as A, and then multiplying those two numbers together. So find the component of B that is in the same direction as A, take the magnitude of those two pieces, and multiply them together. So what I'm interested in, the first step on this, let's put a different color line in here. I am interested in trying to find the component of B that is in the same direction as A. So let's say I'm interested in finding that distance right here from where they intersect to here. That distance is the component of B parallel to A. Sometimes that will be written as, for example, you could write this as B adjacent. So thinking about this triangle, you could think of this as being the adjacent leg of a triangle. This is the opposite leg of the triangle. Some books will write this as B parallel. In other words, I want the component of vector B that is parallel to A. So that's a different way of writing it out. And you could say, well, how do I go ahead and do this? I'll give you one more piece of information, because generally when we're dealing with the graph, I call this my graphical interpretation. When you're dealing with this graphical kind of nature, you're usually given a third piece of information, and that is the angle between the two vectors. And if I gave you a minute and I said, okay, can you write an expression, knowing theta, knowing the magnitude of B, can you write an expression that gives me the parallel component? In other words, B parallel or B adjacent. No, I'm serious. Go ahead and write it on the page. You're taking notes, right? Good. You say, well, wait a minute. I know this. I've got a right triangle here. In fact, you can kind of see it. And you say, well, if I want the adjacent, so I'll write down B parallel here. If I want the adjacent component, what I need to do is take the hypotenuse of that triangle. That's the magnitude of B. And I need to multiply by the cosine of the angle. And there you go. That is the component of B in the same direction as A. Now I said the dot product, you're not done yet. Okay, you're halfway there. I said the dot product is taking the component of vector B that is parallel to A and multiplying the two values together. In other words, I want to take A, vector A, the magnitude, and multiply it by B parallel. This is the final answer here would be the dot product. So put dot product. This is what it's defined as. Or if I took this expression that we just found up here and substitute it in, we could write magnitude of A times the magnitude of B times the cosine of the angle between them. That is the dot product. You're done. Congratulations. Notation issue. Rather than, of course, I'm not going to write dot product every time. How we actually write this notation and making sure to keep the vector signs, and hopefully here you will see why the vector signs are so important. We write this as A dot B. You see, if I forget to put these vector signs on, this starts looking like a regular multiplying of two numbers together, two scalars. So I have to remember that, okay, well, this is not two scalars being multiplied together. This is not a scalar and a vector being multiplied. This is two vectors. So this is how we actually write the dot product. And notice I use a dot. That's why we call it the dot product. Now you might say, wait a minute, Greg, hold your horses. Why am I taking the component of B parallel with A to do this? Why can't I do B dot A? I say, wonderful. Take a minute and figure out if I wanted to do B dot A. In other words, find the component of A that is parallel to B. Go ahead and write that expression down. Of course, you've probably paused the video. I'll go ahead and get at it. Let's look at that. So the first thing I need to do is let's drop a perpendicular from the tip of A to B. Boom, there we go. And I say, okay, well, this distance from here to here, that would be A parallel, the parallel component of A with vector B, or the component of A that is parallel to B. And hopefully you see already, wait a minute, I'm still using the same angle. I have a right triangle right here, this red line, vector A, and then this A parallel. That's still a right triangle. If I want to get the parallel component, well, that's just the magnitude of A times cosine of theta. And then I multiply that by the magnitude of B. And then, of course, because the order that I multiply numbers doesn't matter, I'll just rearrange this, and I end up with the same expression. I end up with A times B times the cosine of theta. And I see that's the exact same answer I had up here. So apparently, the dot product is commutative. In other words, I can do A dot B or B dot A. The order doesn't matter. I end up with the exact same expression. Pretty cool. Now it's from the graphical standpoint. Oh, excuse me. One more piece of information. Forgot about this. The angle that we're using here, note that it's always the smallest angle. I put the two vectors tail to tail. I see that the angle between them is the smallest angle. And please be careful. The number one mistake I see in these dot products is a physics problem that gives you an angle, which is not the angle between the two vectors. Just because you're given an angle doesn't mean it's the right one. Okay? You are forewarned. And frankly, most of the time, if you can draw a quick sketch, that will help save you from some errors. So, that being the graphical case, let's go ahead and now we will move on to looking at the how we do this algebraically. So how do you do the algebraic dot product? And we're not going to go through and derive expressions or prove how this is. If you're really interested, come by my office. We'll crack open a linear algebra textbook. We'll Google some stuff. We'll figure it out. Frankly, I don't remember off the top of my head. What I will tell you, however, is you need to know how to actually do the calculation. So here, excuse me. Here's your vector triplet. So I'll call this AY and AZ. So here's my vector triplet. BX, BY, and BZ. Okay. And again, we talked about the dot product is taking the component of one vector that is parallel to the other and multiplying them. Here in this notation, this triplet notation, you can kind of see what we need to do. I need to take the component of vector B that is parallel to A. Well, I have this x piece, this x piece. Those two are obviously parallel to each other, and so I should multiply them. So if I want to do A dot B, well, this is in the x direction, this is in the x direction. I must have to multiply those two together. But wait, there's more. I also have the y direction. And because the y direction is independent of the x direction, I don't have to worry about any kind of funky cross terms or ax's and by's. I don't have to worry about any of that. I just have to do ay times by and add that to the ax bx. So I've got how much they overlap in the x direction. I've got the overlap in the y direction. I do the overlap in the z direction. And I am done. Happy, happy, happy. I have now got an expression for how to algebraically determine the dot product. Okay. So I'd say this is kind of the algebraic way of doing it. You also have a geometric way of doing it, thinking about angles, magnitudes. There's this. Either one of these will give you the answer if you're asked to find a dot product. And so you say, well, how do I choose? And the answer is part of it comes down to practice. Part of it depends on what information you're actually given. So if you're given an angle, that might indicate that you're probably going to go for this one. Again, but you have to make sure that you know that it's the angle that's between the two vectors. If you're given triplets, this one's the way to go. Of course, my personal favorite is I give you the triplets and I ask you for the angle. And in that sense, then you have to take these two definitions and set them equal to each other to find what cosine of theta is. Okay? So that might be coming up. In fact, you might want to practice that. So to summarize, okay, well, I guess this is my summary. We have our geometric way of doing the dot product. We have our algebraic way of doing the dot product. And again, memorize both of these. You will need them in the future. Thanks for your attention. I'll see you next time.